it takes. Does that make sense?
Because you might have to combine directions.
To be honest, I don't have to. All the work we ever use unit vectors for, we didn't really have to, but it makes it a lot easier if I know it's just a 1.
When you say direction is 1, does that mean that the length of that?
Not the direction, the length is 1. To get the direction, we had a good idea up here.
Oh,
The length of it is 1. So that green vector, let me call it the G vector. How do I get its component form name? What's it based off of? It's based off the what vector? The A vector. What's the A vector? That's too long, so I'm going to divide it by
the norm.
Yeah, the 2.8 we just got, right? I like it. Which norm is the more general word for lengths, because when you start talking about different, what's called metric spaces, if you go there, you can have different ways to define lengths in them. Oh, there's so much cool shit if you go far enough in math. You start to look back and go, everything I did was just one possible thing within one possible construct. Oh, sorry. Sounds a little matrixy, I'm sorry. Yes?
Now you can just, you have the same direction. So basically the reason you would want to do this is so you can just multiply it by whatever.
And you know the direction
it's in.
I love it. And I kind of did this backwards, but I like the fact that it made sense to most of you guys, it seemed, when we talked earlier about the idea of a line. And that, it didn't really matter that this wasn't a unit vector, but if it was a unit vector, it would be not more useful, but then these multipliers would be easier to think of in terms of building blocks of that direction. So I don't want the direction, the thing controlling the direction to have a length, because I just want it to only mean the direction. Then I can multiply by whatever, so I can make it this long in that direction. Does that sort of make sense?
Which is why you make it divide by 1.
Exactly. I divide by the length of what it was so that it becomes 1. Now it only controls direction. It doesn't change the value of something else's length.
That's what I've been asking. So you set it to 1 so that then it's easier to control the length.
Okay, good. Thank you. All right. I'm really sorry if I don't understand the question. Okay. I like it. Everybody with me so far?
Yes.
Oh, man. We got so much happening. Okay. Where am I at? So, and then this would be whatever the hell. You just divide, and you get such stuff. And that would be the new, what is that? That's like 0.9 something or other. Whatever. Blah, blah, blah. And then point, who knows? I don't know. 0.2 something. 2.7?
0.97 and 0.23.
Ah, all right. Went the wrong way.
Or 4.
Sure. Blah, blah, blah. All right. Let me just stop there for a second. How we doing? 0.24, you said, roughly? So obviously, if I found this guy's length, what would it be? 1. It's got to be. Why? Because we made it so, right? It wouldn't be a surprise. We made it that way. Let me let all that sink in. Yes?
So, G is the unit vector?
Yeah, I'm calling G. They didn't give it a name, but the little green direction, that I'm just calling it G for green. Yeah. That's the name for that. Now, real quick, just because it came up, how would I find it's the angle of that, which is another way to define its direction? How would I find the angle for that G, that angle between the x-axis and that green line?
The 2 sides of the arc.
Yeah, exactly. You're going to see a lot of overlap between the conversions between x and y and the polar coordinates, because that's all this really is at the moment, right? So you're going to see a lot of overlap with those two things, because it makes sense. That's basically the same thing. Arctangent of who to what?
0.24 over 0.97.
Yeah, and in fact, it doesn't even matter if you use this, or this, right? Can anybody tell me why? Why does it not matter if I use these or these? The ratio is going to reduce the same thing. Who cares? It doesn't matter. So then you can do this arctangent and tell me, if I do this or this, it's going to be the same thing. I'm going to use these numbers because I'm more sure about those numbers, because those are the actual freaking numbers. Right? And then whatever you get. So I don't know. Somebody got that for me just because? It looks like it should be decently small. Maybe close to 5 or 6 or something. Maybe do degrees.
0.24.
0.24 radians.
Yeah, radians.
All right. Which is roughly, it's like, that's like 45 degrees.
It's like
13 degrees? All right, I went the wrong way. 13 degrees. That looks more like what that is, right? I like it. Kick ass. All right, so we had a lot of stuff going on there, but the nice thing is there's a lot of overlap with this section and stuff you already know, which is always nice. It's not all brand new. What's brand new is we're calling them vectors, we're moving them around, and now we're talking about vector algebra, how to add them. The next thing we'll talk about how to subtract them, stuff like that. So here's the picture for how to add them. Does it make sense? Thank God. I like this one because I can move it. So if I click that there and I click that there, I get a nice, good old rectangle with all the normal stuff. But of course, now here's the thing. In this respect, it's very easy to see, how do I add 0, 2 to 4, 0? Does it not make sense that the answer would be 4, 2? Because if I go 4 in this direction and then 2 up, what point will I end up pointing at? The point 4 freaking 2, right? But the beautiful thing about vectors is it doesn't even matter how many dimensions they exist in. To add them, I just add them, right? So how would I add up here the u and the v? How would I add, what's u plus v going to be?
1 plus 3.
4, negative 1. And does that look about, that's actually pretty good for me, to be honest. Doesn't it look like it's 4, negative 1?
Yeah.
Just almost? With my horrible scale, it's actually really damn close considering that. Right? That's just, sure, thank you. Christian, you're within so much of an error tolerance. For you, that's good. I appreciate that. But that's beautiful. Good Lord, you can't help but love that. Not everything's going to be that easy, sorry. How about subtraction? So I know how to add, and it doesn't matter, obviously, what angle they're at. They don't have to be a beautiful rectangle. They could be at any weird angles to each other in any quadrant they want to be in. But again, do you see how, now I kind of wish I could control how much of this shows up. But do you see when in the yellow, that's the actual vector? So if I take this vector and move it here, so I tell somebody to go here and then go back this way, it's the same thing as them just going this way, as the crow flies, right? You guys heard that phrase? Maybe. It's like, why the hell did you tell me to go all the freaking way down there? They were just going to come all the way? How could it just went there? All right.
You're not.
Huh?
You're not a crow.
Not a crook?
You're not a crow. That's why I told you.
Oh, crow. I'm not a crow, exactly. Not today. Okay. All right. So, what about subtraction? How would subtraction work? Well, does subtraction exist? No. Subtraction doesn't exist. Come on. There is no subtraction. There is no division. Oh, I love the looks on your faces. Subtraction is just adding the opposite. Now, of course, you could start, if you know how to add things, then that means you know how to subtract things, especially if you know how to multiply. So if 2u is twice as long as u, what would negative u be?
Just the opposite direction.
Yeah, how long would it be? Negative u.
Same length.
Same length, just pointing in the opposite directions. Here's u, negative u would point this way. So if I wanted to do u minus v, I would do u plus negative v. Let me stop there for a second. Does that make sense? Of course, hopefully it does. Now, but there must be a more direct way to find it than doing that. That's not that hard, but still. So, here, if I wanted to do u minus v, all I would do is 3, 2, minus 1, negative 3, or I can make it 3, 2, plus negative 1, 3. That's amazing. So computationally, it's easy as hell. But what does it mean visually? So the nice thing with addition is, it's sort of, do you see how this is the diagonal of this parallelogram that it creates? So that's beautiful. So it's a beautiful geometrical interpretation of the addition of two vectors. Holy crap. It's a long statement. I want a beautiful representation of the subtraction of two vectors, right? And unfortunately, the word beautiful doesn't normally apply to anything I draw, but this is kind of nice. Now watch this. I wish I had one more color, but it's too bad I don't.
Yeah, green.
Where's green?
Behind you.
Oh, sweet. I wish I had $4.8 million. Shit. All right. I should have said that first. All right, so here. So if I want to do u minus v, then that means, what's negative v going to be, very specifically? V is 1, negative 3, so negative v is? Negative 1, 3. I like it. Shwa! And if I add these two, it would be here, right? I like it. Are you guys with me? But notice, now real quick, and it's going to start here, and it's going to end here, right? Now this is nothing, this is not detailed enough to say that's the answer or anything. This is just a quick visual of what's happening. The actual work is easy, right? But I want to show you, relative to these, where is that answer? Well, remember, I can pick vectors up and move them around. Wherever the result of something I do is just where I happen to think about it being. It doesn't have to, I really want this all to make sense. So relative to these, isn't that just this here? Isn't that just too nice to believe? That the addition is this and the subtraction is this. What direction is that vector, that resultant vector pointing? How do you say it? Don't say up. In relation to u and v, who's it pointing to? And notice how u was the first vector in my... So if it was v minus u, it'd be the same damn vector except to be pointing in the direction of v. Let that be freaking awesome. Let that be beautiful. Let that be nice. Let it be... We'll see. All right, good. My hardest part about this whole, I think I've already said this, is just figuring out what order to do all this stuff in for you. It's not difficult math, but there are a lot of cool little things that you couldn't necessarily plan for that happen. It's really nice. I don't think they show you a nice visual of that. No. Oh well, too bad for us. Oh. One more thing I want to say about subtraction, just to see it, because I like this visual. If I have a vector sitting here, what would you say this is? That is the what of that vector. So you guys, here's y piece. I love it. The y component. I love it. So if I subtract, let's call this let's call it its own thing. That's the vector v. So if I do u minus v, the resultant should be the x component. Doesn't that just make sense? And sure enough, if I just look at this visually, I don't even have scale drawn here. But if I subtract these and I know how to draw them, the addition would be down the center. The subtraction would be, if it's u minus v, it points in what direction? Towards the u vector. So it's going to be this. And that's the resultant. That's u minus v. And it makes so much freaking sense because I just took out the y piece. So the x piece should be left. So y isn't on the x-axis because I didn't draw it there. If I wanted it to be there, I could just draw it there. I could move these things around, which is going to be a little bit of something for you guys to get used to. Why did the answer end up here? Because I left these where they were. If I would have done this, u plus negative v. Do you see that? I really want this to make sense, what I keep saying. U plus negative v. Wouldn't the answer have been on the x-axis?
Yes.
Do you see why it doesn't? That where it ends up is not itself a part of the answer. Always. You can put it down because it depends on how you set it up. So geometrically, it doesn't matter that it ended up here. It could have ended up there if I would have done it this way. Ooh. So that's why you can move these vectors around.
If you did it the second way, would it be pointing towards negative v instead of negative v?
No, because, how would this make sense? U plus v would be this, right? So u plus v is not as hard to think about where it points. It just points to where you end up. So if I did u plus negative v, isn't that where I end up? I end up here. So then I would point in that direction. So there's nowhere near as much seeming ambiguity with addition. It just points to where you end up. Subtraction is kind of like, well, which way does it point? Right? It's a little bit more ambiguous, but now it isn't. It just points in the direction of the first dude. Gotta love that. Or dudette, I can't tell. The biology of vectors. Whole other class. Well, some of you guys are like, is this going to be a test? What the hell? Have you seen what's that? Turn it over. All right. Sorry. Oh, let's see. Where do I go? All right. Blah, 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 blah. So taking a step back, let me see if I said everything I want to say. Blah, 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 blah. I love it. Okay. Okay, cool. That's the first part of section 12.2. I want to take a step back, go to 12.1, because 12.1 just introduces 3 dimensions. Not a big deal. But I do want to point out a couple things. So here's our standard, 2-dimensional thing. Why did we pick, real quick, before I even do that, this is going to blow your mind a little bit. But the choice, if I draw the x-axis, okay, there's the x-axis, yay. Now, to be honest, to find points in space, I could draw the y-axis like this. There's no damn reason at all that the y-axis has to be perpendicular to the x-axis to identify points. That might freak you out a little bit, I don't know.
Not really, but if you want to be able to change a y-coordinate of a point without changing an x-coordinate,
There are some, yes, totally. This would be a remarkably strange problem that doing this would make it easier, right?
Yeah.
I'm with you. But there are problems where I'd rather change my coordinate system than change my equations or symbols that I'm using, because that actually makes it easier, to be honest. It's kind of weird. But this is not done very much. The only point I'm trying to make, the only way I can't draw the y-axis, so I wanted to find this point, then I just have to go, see how now it's everything slanted, right? But still, this is still, so if I want to find that point, I just have to go up far enough, it's somewhere in between there, and then the x-axis and the x part would be that. So I can find any point in 2D space with axes that are at a whatever angle that is. Maybe it's 45. Doesn't matter. As long as the two are not 0 or 180 degrees, because then you can only find something on that axis then. Is that sort of understood? I know this is something, I don't know if you've ever thought about it or been shown this. The fact that they're perpendicular is really just so that I can make transformation and other things easier, right? Because it's pure y, pure x, not mixture and then pure, oh shit. So my point with this is, if I want 2D identification of points to be easy, I use perpendicular axes, right? And in fact, what the hell is this? These are both lines.
Linear independent.
So, I love it. So they are linearly independent. Look at that linear algebra stuff sneaking in. Where'd you hear those words? I can't remember.
DPQ.
Okay, great. You've taken, so how many people have taken, that's right, keep forgetting, Calc 3, so many guys have taken DiffQ, maybe even linear algebra. Anybody taken linear algebra? Kick ass. DiffQ? DiffQ, anybody else DiffQ? A few of you guys, and the rest of you are like, no. Okay. Beautiful. So it's linearly independent because they don't have, neither one of them have components of the other. They're not a mixture of both, right? So that makes sense, that I want to have perpendicular so it's easy. So if I want to go to 3D, I need something that's perpendicular to both of these. And of course it's easy enough because we just go into 3D, right? The little point I want to make is, to define the x-axis, I can actually use a vector that denotes that direction. And how long do you think that vector is going to be? Holy shit, no. 1. If I want something that only means direction, I don't have to make it 1, but if I can, I will, because that makes everything else easier. They're little building blocks then. So what we call this the I vector, and sometimes we don't use a little thing, we just use a little hat on it, or I will anyway, because that's the way I was taught back in the day. Anybody know what this one's going to be called?
J.
No way. Holy shit. And then the one that I can't draw based on how I've drawn this, but normally if I want to draw 3D on a 2D plane, I do it, well, I guess I could have just added it in there. But this will be the x-axis, y-axis. We like to consider the xy plane to be like my ground that I'm standing on, and then the z-plane somehow the above and below. As above, so below. Okay. It's a good movie, actually. And this will be the z-axis. So this is my I, this is my J, and this is my, remarkably enough, no way. Okay. See. Okay, I like it. Nice enough. And I think some of you guys have seen IJK possibly before. We're not quite to cross products yet, so don't start throwing those out yet. All right. I like it. So let's try, here, you guys go with me here. Let's try to plot the point 2, -1, 3. Let me make it a point. Let's not make it a vector. Bam, bam. You'll quickly see how this is difficult because of perspective, but oh well. X, Y, Z. I think before I get too far, did they talk about this? Yes, cool. So one reason why we put this, I don't put X here and Y there, is there's something called the right-hand rule. So there's actually a left-hand rule and right-hand rule for various things. In physics, it has to do with force on an electron, possibly, and in a magnetic field, stuff like that. But if I put my X along there and I curl in the direction of Y, my thumb will point in the resultant direction that the other guy's got to hold. So to hold that, to make that true, that right-hand rule. So the Z's got to be up that way. So if I put my hand along the x-axis and curl it in the direction of the y-axis, then my thumb points in the direction that I should put the z-axis, the positive part of the z-axis. I like it. And there are a lot of different variations on that, by the way. Sometimes there are some where they say it's pointing out of your palm. There's all kinds of variations. Yes?
Will we get marked down on the homework if we switch the axes, or the x and y ones?
Yes, because then you've made sort of a mirror dimension, right? So that'll freak me out. I don't know if it's the Stranger Things, Underworld, whatever. What was it called? What was it? Have you watched Stranger Things?
Yeah, upside down.
Dude, watch it. Of course, I'm an 80s kid, so it means even more to me. Sorry. It was really good. It was really good. All right, so how do I graph 2, -1, 3? So I got to set up some... This thing's a little getting used to, doing by hand. All right. What's up?
Don't you want, if you do put a grid on there, would you want the grid so that each element, like each of those little divots on your x and y, shouldn't those be parallel to the, like for the y, shouldn't they be parallel to x? For x, shouldn't they be parallel to y? So they're pointing together.
Oh, yeah. You're right. Thank you, Christian. For a minute, I was like, what the hell are you talking about? So yeah, this is going to have to be in this plane, the xy plane. Thank you. I wasn't even thinking about that. So you've got your xy plane, and you've got your z coming through it. So 2 is on the x-axis. Down 1, back 1 on the y. Right. So these actually should be more flat, like this here. Well, I think that's exactly the same way you just did, Jim. Hold on. So 2 on the x, back 1 on the y, and then up 3. This is where things get really weird. Up 3, 1, 2, 3, roughly. So everybody's going to have their dot in a different place, possibly. And if I just put that on the board, I said, what point is that? That would be really difficult to identify. Just like anything in 3 dimensions. I mean, it's difficult to know. If you look off in the distance, you're like, exactly how far away and how high up is that? I don't know. If I knew how big it was, maybe I could tell you. Right? Yeah.
If we lived in 4 dimensions, it would probably be a lot easier.
Oh, we do. We live in 10 dimensions, at least. Anyway, we won't go there. All right. So, thankfully, I'm not going to make you do a ton of these, but I did assign several that will have you doing this. I will not expect it to be perfect, obviously, right? But I have to get you to try it. I know technology can do this for us, but we have to have a more intimate connection to it. So I'm a kind of an old school kind of guy, as those of you who have taken me before, you know this, because the new school stuff has you less connected to the math, and that's bad. Okay. Doesn't mean I don't mind using new school stuff to help look at this, because it's weird shit. Oh, all right. So a little consequence of this, I think when I taught my pre-calc, I was talking about, we didn't even talk about 3D yet, but I could define something to be a spiral as long as I bring in that 3rd dimension. Let's not go quite there yet, because it gets a little weird, but like for example, what would this be an equation of in 2D? Circle. if you graph that here, it would be radius 1, and it would be all on the xy plane there, right? So that's not too bad for me. And of course, the reason that 3D is so hard is it's hard to tell, which way is this thing lying? Is it an ellipse? No, it's a circle that's on this weird slanted plane. You guys, so that's the xy plane. So what would that look like in all 3 dimensions then? Yeah, because what's the restriction on z? So for z equal to 1, it's going to repeat this image. So it's a circle at every level of z. So yes, at the end of the day, it's going to become this. So it's going to have another circle here and another circle there. It's going to become this cylinder. I sort of gave up on it there a little bit. But they have a much better picture, an actual cylinder created by a computer on page 834. But that idea, if I'm missing a variable, but I'm in a higher dimension that includes that variable, it's just going to continue that same shape in that direction. We've seen that before, right? Maybe. So what about this? See, yeah, sure. I like that. Ooh, so what plane can I draw a trace of this, a cross section of this in? What plane does this live in primarily? The what plane? What plane did I start this one in? XY, because it's Y. So what plane am I going to start this one in? Well, crazy. All right. So y equals z squared. So let's see, x, y, z. So if you just draw it in the yz plane, I picked that to be nice because it's like our normal plane we're used to. Do you understand what I mean by that? Because that's the one that's like head on a little bit. How are we doing? All right? You guys still looking? Okay. So therefore, how would I do this? Y equals z squared. When z is 0, y is 0. I like it.
Parabola.
Yeah, it's parabola. But now you just got to be careful about which way does it open and so forth, right? When z is 1, y is 1, right? And when z is -1, y is 1, and so forth. So it's going to be the parabola, and then how is it going to be from there? How do I get a complete kind of picture of this? Yeah, it's going to extend forever in both directions, right? Not for me, it's not that bad. So it's this, oh, that's horrible actually, John. Oh, I'll get over it. But it's going to be this, like this in all directions, like, right? Yes, sort of like a, if you took it and laid it down, it'd be like this. Forever. I like it. All right, good. So what gets more interesting, of course, these are like open-ended, which is easiest to get into for 3D because I can just draw the 2D and then extend it. What gets more interesting is when I have these closed. So the sphere is easy, but what does it look like when I have, if I introduce like plus x? Now that's going to be somehow more closed because now it depends on the x. So, we're going to build up to that point. We're not quite there yet.
Well, that'll just go diagonal.
Yeah, so you're going to have to do what's called these traces in the different planes will help you get the full picture. So that's coming later in the semester, but you can already start to imagine how to piece it together. This was a trace repeated. I'm going to have to do multiple traces in each plane to help me figure out what it's going to look like if I have all 3 variables in that function, in that equation. All right, maybe. And then they talk about the distance formula in 3 dimensions. We already know that. The equation of a sphere in 3 dimensions, we know that. Blah, blah, blah. And then you got infamous number 46 to work on. Okay. Let me see. Blah, blah, blah. So now that I've sort of introduced something that you already know, I feel a little bit more at ease talking about 3-dimensional vectors. But everything we talked about in 2 dimensions basically extends to 3 dimensions for vectors, right? How to add them, how to subtract them, so forth. It's just a little bit harder to graph them, right? To show them graphically because of the inherent problems of 2D paper with a 3D image. Not easy. Let me make sure I don't skip anything. Blah, blah, blah. Oh, already talked about that. Sweet. Yeah. I think we basically finished 12.2. Let me make sure. We got the IJK stuff in there. The only thing we haven't really finished is What's A minus A?
Zero.
Yeah, it's the zero vector, which is a weird idea. But the zero vector is just a zero length vector. And I talked a little bit about last time when I said the winds were 0 mile an hour from the southeast. And you're like, what does that mean? You know what the wind wants to do. I want to go that way. Yes?
So is it like direction?
In a sense, there are situations where you can actually give it direction, to be honest, but it has to have other things happening to make that make sense. But fundamentally, no, has no direction. Yes? In some situations, you can consider it to be that way, but it really has no direction. You can define a direction in a certain physical case.
Checking with a dot on that plane, but the thing is, like, it's the vector past this and this. I remember somebody telling me that it's
And again, it totally depends on the way you want to look at it, to be honest. But the zero vector is almost kind of silly, because if it has no length, it technically can't point anywhere, right? It can't have a direction vector because its length is 0, so its direction vector would be, in a sense, undefined, wouldn't it? Try to divide it by its length, and it's undefined. So in that sense, you can realize there is no defined direction for it. But in some cases, I understand what you're saying. Again, the way you look at something can help you do other things with it. Okay, I like it. Maybe. What else do I want to say? Oh, some of these things are just kind of silly. What do you think about this here? What can you say that's the same as?